Power takes form at Morandini, where heavy-duty metal structures are shaped for industrial strength. Red-hot billets are lifted from the furnace and positioned beneath massive hammers that strike in steady succession, compressing metal grain by grain into its intended form. Each impact feels like raw power being sculpted into purpose. After shaping, the forged pieces are trimmed and straightened for exact dimensions, then cooled under controlled conditions to retain durability. This balance between heat, pressure, and precision defines why forged steel stands unmatched in resilience. No. In the world of precision machining, the Okuma Multus U3000 demonstrates how complex parts are brought to exact specifications. The process begins with setting the B-axis swivel, adjusting angles from 95 degrees to -10 degrees, allowing tools to reach every critical surface. Sorting is crucial, as even minor misalignments can affect the final gear geometry. Operators monitor the initial setup to ensure consistent engagement of the cutting tools. Toolpaths are programmed with detailed simulation to prevent collisions and optimize cutting efficiency. Spindle temperatures are constantly monitored to maintain consistent cutting conditions. Dynamic load adjustments help protect the machine and extend tool life. Using a VCMT 160408 insert, C45 steel is cut with a depth of 0.5 mm at a feed rate of 0.25 mm per revolution. Every pass removes material while maintaining the integrity of the gear's dimensions, a testament to the machine's stability. The ID skiving roughing step tackles gears with modules 2 and 4, progressively removing material across multiple cuts. Cutting depths range from 0.3 to 1.76 mm, with spindle speeds adjusted from 1035 to 3696 minutes to optimize efficiency. Observing the precise synchronization between main and M spindles highlights the advanced engineering behind each motion. Finishing cuts refine the gear teeth with minimal depth and feed rate, ensuring surface quality and dimensional accuracy. Integrated NC gauge measurements assess roundness, diameter, and taper angle, confirming that each component meets strict standards. Power skiving operations complement the B-axis turning, removing residual material while preserving the intended geometry. Regular monitoring of tool wear and spindle performance keeps production reliable. Automated tool changes reduce downtime and maintain a continuous production flow. Continuous adjustments and NC feedback guarantee consistency across production batches, demonstrating the machine's versatility and precision. Each finished gear reflects the integration of human expertise with machine intelligence. No ordinary machine could handle stainless steel this precisely. The DMG Mori NTX2500 takes that challenge head-on. Designed for full, six-sided turning and milling, it crafts a surgical hammer with both strength and refined geometry. Each hammer begins as a solid 1.4057 stainless steel bar, 80 mm thick and 300 mm long, locked firmly in the chuck before machining starts. NTHE turning operation removes excess metal, shaping the cylindrical body and smooth contours. Crazy how fast this machine completes a part that complex. The automatic tool changer then brings in the milling spindle, which carves the detailed head and balanced neck in one uninterrupted motion. Even the smallest curves are rendered with flawless symmetry, and once one side is complete, the part is repositioned for the opposite faces, keeping tight tolerances across all 6 sides. Hard to believe it only takes 2 setups for full machining. Final polishing and deburring leave every edge smooth enough for surgical use. No wasted motion. Every tool change counts. None. From tightly wound coils to precisely stacked bundles, every action ensures the steel is ready for transport and processing. Each coil is lifted vertically into a compression unit, where hydraulic plungers lower to press the loops, reducing height and tightening layers. This step ensures bundles remain stable for storage and transport, highlighting how engineering solves space and handling challenges. Pressure sensors control the compression automatically, applying consistent force to each coil. After compression, coils stay centered between steel columns while vertical lifts and rollers raise and align them for inspection and labeling. Rotation and guided shifts prepare the bundle for offloading. A mechanical lifter then transfers the coil horizontally onto rail conveyors, which carry it to the loading bay alongside dozens of others, ready for shipment. Shock absorbers reduce vibrations during movement, protecting both the steel and equipment. Operators constantly monitor alignment and intervene when necessary, blending human oversight with automated efficiency. Every coil moves with control and balance, demonstrating how massive weight is managed with finesse. The Profi Turn H by Waldrich Siegen begins shaping crankshafts with remarkable surface quality and efficiency. Each blank is precisely secured, allowing the lathe to remove material evenly. Operators monitor cutting parameters, ensuring consistent dimensions and smooth finishes across every workpiece. The balance between speed and control highlights the machine's engineering excellence. The 5-axis auto-tuning system of the Okuma Multus U3000 drives precise turn-cut machining with remarkable consistency. Each workpiece is carefully secured, while the tool laser measurement ensures absolute alignment before machining begins. The touch setter verifies tool positions, minimizing errors during complex cuts. Every adjustment and calibration reflects the precision engineering embedded in the machine. Operators oversee the process, noting the smooth synchronization between axes as the lathe executes intricate operations. The system allows simultaneous turning and milling, maximizing efficiency without compromising quality. Observing the automated corrections and fine-tuning showcases how technology and operator expertise combine to produce consistent, high-quality components. Crushing force and glowing heat define the heart of Singler Forging Private Limited, where raw steel is sculpted into high-strength components. Each blank aligns under the forging press, and powerful dies stamp intricate features onto the metal. Operators carefully monitor alignment and pressure, ensuring uniform quality across every piece. Even as steel bends under extreme stress, its response is predictable, showcasing the synergy between material properties and skilled control. Finished forgings move on to cooling and inspection, ready for the next stage of production. Watch the careful alignment and secure fixation of compressor screws at Singler Forging, where every movement ensures flawless performance. Each screw is carefully positioned within its housing, ensuring rotational accuracy that directly affects airflow efficiency. Operators inspect each screw visually for micro-imperfections before final fixation. Inside the facility, stainless steel components begin their transformation through electropolishing. The atmosphere feels charged with anticipation, as racks of parts are prepared for treatment. First, the parts are mounted and immersed in a temperature-controlled electrolyte bath of sulfuric and phosphoric acid. Direct current charges them positively, and the solution conducts electricity, dissolving a thin layer of surface metal. It is striking to think that just microns removed can reshape performance so dramatically. Next, the surface is leveled, leaving behind a bright and passivated finish. The change in texture is immediately noticeable, catching the eye with a smooth uniformity. After treatment, multiple rinses remove residual electrolyte. Components are then dried, inspected, and packaged. Every step builds assurance that the steel will endure in harsh environments. The process balances chemistry and engineering in perfect harmony. Each detail reflects a quiet strength hidden beneath polished surfaces. The Haas ST20Y lathe engages in a dynamic demonstration of turning and milling operations, showing the capabilities of live tooling combined with Y-axis travel. Engineers handle the machine with a focus that highlights the complexity of off-center milling and drilling. The precision of each cut reflects the skill involved in handling sophisticated CNC machinery. The first action positions a raw metal workpiece in the chuck, securing it for the upcoming machining steps. The spindle, powered at 14.9 kilowatts, accelerates to 4,000 revolutions per minute, delivering 203 Newton-meters of torque at 700 revolutions per minute, while the hybrid 12-station turret prepares for tool engagement. Milling starts with the Y-axis offset, allowing precise off-center cuts, holes, and taps, reducing the need for repositioning the part. Drilling operations follow, using live tools to navigate tight spaces without interrupting the turning process. The synchronization between the machine and operators demonstrates efficiency at every stage. The lathe shifts seamlessly between turning and milling, demonstrating multitasking efficiency that minimizes handling time. Engineers monitor the process via digital controls, ensuring consistent quality. Small adjustments are made on the hybrid turret, aligning tools for exact cuts. As each section is machined, the workpiece gradually assumes its designed dimensions, with every rotation of the spindle contributing to accuracy. The smooth coordination of the machine and operators underscores how modern CNC technology elevates both speed and quality in metalworking. Finally, finished components are removed, inspected, and prepared for the next production stage, exemplifying how integrated operations can enhance throughput and maintain high standards across complex machining tasks. Automation drives the ring rolling machine to perform dual-stage shaping with efficiency and control. Engineers operate the system with confidence, showing how automation enhances productivity and consistency. The first step involves loading the raw metal blank into the machine, where clamps secure it for the rolling process. Rollers engage with the blank, gradually shaping it into a circular profile while maintaining uniform thickness. As the ring rotates, profiled rollers press along its circumference, forming the desired inner diameter and contour. Sensors continuously monitor the process, adjusting roller speed and pressure to ensure consistent dimensions across the ring. Once the first stage completes, the ring moves seamlessly to the second stage, where additional rolling refines the profile and enhances structural strength. The smooth synchronization between stages illustrates the efficiency of integrated automation. Operators oversee the entire sequence via digital interfaces, confirming tolerances and surface quality. Any minor adjustments are made on the fly, demonstrating the machine's responsiveness. After final rolling, the ring is removed, inspected, and prepared for the next stage of production. The combination of multi-stage rolling and automated control highlights how modern machinery reduces handling time while achieving precise, repeatable results. The process emphasizes not only efficiency but also the careful engineering behind each component. At the heart of Brazilian engineering stands the Belo Monte hydropower project and its colossal Francis turbine rotor, built by Andritz Hydro. Fabricated in Araraquara, São Paulo, this 316-ton masterpiece required over 2 years to complete. Transporting it was a mission of endurance and planning. 494 kilometers by road to Santos, then 500 kilometers by sea to Belém, and finally 600 kilometers through the Amazon rivers. That scale alone feels unreal for a single piece of machinery. True commitment turned this journey into an engineering triumph. Nanan. The process of feather hemming demonstrates how metal sheets are transformed into precise folded components without interruption. The operation begins with positioning the sheet under the punch and die, preparing for a 90 degrees bend. The high-height bolt system ensures consistent force distribution, allowing even thick materials, such as 1.5 mm stainless steel or 2.3 mm iron, to bend smoothly. Each movement highlights the interaction between tool design and material behavior, emphasizing the sophistication behind continuous hemming. Once the initial bend is complete, the process transitions into the flattening stage, compressing the folded edge to achieve the desired hem. The double-deck die structure enables sharp angle bending and subsequent flattening without changing the tooling. This eliminates downtime and ensures that each component maintains uniform dimensions across production runs. Operators monitor material flow and hem quality to prevent misalignment or surface defects. The machine adapts to complex corner hems and split hems, accommodating varying sheet geometries. Specialized design prevents slipping even when working with stainless steel or colored steel sheets, ensuring reliable hem formation. The punch and die maintain precise alignment while gradually applying pressure, allowing metal fibers to compress without tearing. Continuous monitoring of force and position secures consistent quality throughout the run. By combining high-height bolt technology, double-deck dies, and careful control of bending sequences, feather hemming allows efficient, uninterrupted production of accurately folded metal parts. Each finished piece reflects the balance of mechanical engineering and operator expertise, demonstrating the efficiency of modern hemming techniques. Every piece of steel we use, from bridges to skyscrapers, starts with an intense transformation. At ArcelorMittal Poland, that transformation is brought to life through heat, force, and chemistry. NTHE cycle opens in the scrapyard. Mountains of recycled steel are sorted and loaded into massive charging buckets. Each batch is analyzed to ensure the right mix of iron, carbon, and alloys. Every heap of scrap here represents countless old machines, vehicles, and beams reborn into new structures. These are lifted into the electric arc furnace, where electrodes deliver immense electrical energy to melt the metal. Sparks rise as molten steel forms, a vivid example of controlled energy at work. Technicians constantly monitor the arc temperature to keep the melt uniform. Even minor variations in heat can affect carbon content and final strength. That's why sensors around the furnace feed live data to control systems adjusting parameters in real time. The entire operation depends on both brute electrical power and fine-tuned chemistry. When the melt reaches the target temperature, samples are drawn and tested immediately to verify composition. This early precision ensures that the steel made downstream meets structural grade standards from the very start. Once molten, the steel is tapped into a ladle and transferred to the secondary refining station. Here, alloying elements like manganese, chromium, or nickel are added to adjust strength, corrosion resistance, and hardness. Impurities are removed using slag, which floats on the surface and is skimmed off. The temperature, composition, and cleanliness are continuously measured through sensors and samples. You really get why steelmakers call this the liquid stage of precision. Next, the molten steel moves to the continuous casting machine. It's poured into a water-cooled copper mold, where it solidifies into a long slab. The strand moves downward, supported by rollers that maintain its shape as it cools. The slab is then cut into manageable sections by an automated torch. The engineering behind keeping tons of molten metal stable while cooling is just wild. And after casting, the slabs are reheated in furnaces to regain plasticity for hot rolling. They're passed through a series of high-pressure rollers that elongate and flatten the metal into the desired thickness. Each pass reduces the cross-section and increases uniformity. Surface scales are removed by powerful water jets to leave a clean finish. The sheer force of the rolling mills is unbelievable. Pure mechanical muscle at work. As the hot strip exits the final stand, it's cooled in a controlled pattern to achieve specific mechanical properties. It then moves to the coiling station, where the steel is wound into giant coils ready for inspection. Sensors check thickness, surface quality, and straightness. Once approved, the coils are tagged and stored for shipment. NTHE journey doesn't end there. Many of these coils will later be cold-rolled, galvanized, or shaped into automotive parts, pipelines, and construction profiles. The cycle of steel continues endlessly, connecting industries, cities, and people. And steelmaking at ArcelorMittal isn't just a process, it's a system built around precision control and sustainability. Advanced filters capture dust and gases, minimizing emissions and energy loss. Scrap recycling reduces the need for virgin ore, creating a closed loop that supports global decarbonization efforts. And from scrap collection to molten metal, casting, rolling, and finishing, each stage is guided by data and experience. What leaves the mill is more than a product. It's material reliability for decades ahead. In every structure that stands, in every tool that lasts, a part of this transformation lives on. Is Min. The strength of modern industry often relies on what can't be seen: seamless steel pipes built to withstand extreme pressure. At Armisan, every tube begins its life as a solid steel billet, heated to forging temperature, turning raw material into something that carries entire systems of oil, gas, and water. Hard to grasp how much energy is needed just to prepare one billet for this process. Once heated to glowing red, the billet is pierced through its center using a rotary piercing mill. The rotating rollers and mandrel shape the solid core into a hollow shell, forming the foundation of the seamless pipe. The coordination between pressure, temperature, and rotation defines its strength and integrity. Wild how one continuous push transforms a solid bar into a perfect hollow form without any welding. NTHE hot shell then moves to the elongator and stretch reducing mill, where it's lengthened and its wall thickness adjusted. Multiple rolling stands compress and stretch the metal uniformly, achieving consistent diameter and surface finish. Operators monitor every pass, ensuring the pipe meets strict dimensional tolerance. You can tell this step decides whether the pipe can survive real industrial stress. And after hot rolling, the pipes enter controlled cooling beds, where they regain structural stability. Once cooled, they undergo straightening, trimming, and marking for traceability. Surface inspections detect any deviation before heat treatment restores the ideal mechanical properties. Crazy that every single piece must go through inspection before it's even close to shipment. NTHE heat treatment furnace tempers and refines the steel, improving its ductility and toughness. Pipes are then tested hydrostatically under pressure, far exceeding real-life conditions to guarantee safety. Dimensional and ultrasonic checks ensure no hidden flaws remain. Makes you appreciate how much unseen quality control lies behind something so ordinary looking. And finally, the seamless steel pipes are bundled and prepared for customers in energy, construction, and heavy manufacturing. Built to perform in the harshest conditions, they represent a perfect synthesis of heat, force, and material science, the quiet backbone of modern infrastructure. In deep-sea oil and gas systems, reliability can't be optional, and this giant spring is proof of that. Made from a steel bar almost 3 inches thick, it's engineered to endure the crushing pressure of the ocean floor. Wild to think one coil of steel can carry the load of an entire subsea structure. NTHE steel rod is first heated in a furnace until it reaches the austenitizing temperature, where its internal structure transforms to allow maximum strength and flexibility. Once it's glowing, the bar moves to the coiling machine. Massive rollers grip and bend the metal around a mandrel, forming it into the large spiral that will serve as the spring. Hard not to respect how much force it takes to bend steel that thick. And after coiling, the red-hot spring is quenched, rapidly cooled in oil to lock in its hardened form. The quenching medium and timing are tightly controlled to prevent cracking and maintain uniform properties. Every second here decides whether the spring survives or fails under deep-sea pressure. Next, the coil undergoes tempering, reheated at a lower temperature to balance strength and ductility. Dimensional checks and surface inspections follow before final testing simulates real subsea stress conditions. Adian, reset. The journey of steel coils continues as they enter forming and welding stages for high-quality pipe production. These strips are fed into the pre-forming section, where rollers gradually shape them from flat steel to a tubular form. The continuous process directs the tubes to the high-frequency welding station, fusing edges into a solid seam. Excess material is immediately removed, and the welded strip is cooled with emulsions before ultrasonic inspection. Next, medium-frequency currents relieve stresses in the weld and adjacent areas. Air and emulsion cooling prepare the tubes for calibration, shaping each pipe to exact diameters. Square or rectangular profiles are formed from round tubes when requested. The tubes then move to the cutting station, where they are cut to customer-specified lengths. Subsequent finishing removes residues and performs end cleaning. Pressure testing for heating or fuel transport pipes confirms durability, followed by a second ultrasonic inspection to verify weld integrity. Automated stations weigh, measure, and mark each pipe before sending them to storage. The combination of modern machinery and coordinated operations demonstrates how industrial innovation and skill maintain quality and efficiency throughout the production. Video showcases a dry cutting process for bevel gears, specifically the M5.5Z22 model. The steel workpiece is clamped, ready for material removal along the tooth profiles. As the machine engages, excess material is cut away, gradually shaping the precise bevel geometry. The whirring of the cutter adds a sense of controlled power to the operation. After the initial cutting pass, the gear is repositioned for additional passes, ensuring complete profile formation. Cutting parameters are monitored to maintain consistent tooth spacing and surface finish. Careful observation shows how small adjustments can significantly improve the final outcome. The dry cutting method reduces coolant use, lowering both environmental impact and operational costs. Operators can observe subtle variations in cutting load, adjusting settings to optimize results. Every rotation of the cutter highlights the machine's reliability and the operator's attention to detail. Once shaping is complete, the bevel gear undergoes thorough inspection. Tooth angles, spacing, and surface integrity are checked against strict specifications. Minor corrections are applied as needed, maintaining high-quality standards. Seeing the finished gear ready for assembly underscores the skill and coordination behind each step. Finally, the finished gear is cleaned and prepared for assembly or shipment. The process emphasizes efficiency, sustainability, and precision in manufacturing. Seeing the entire workflow underscores how careful setup, tool selection, and monitoring can produce durable, reliable components with minimal waste. Dry cutting offers a blend of speed, accuracy, and reduced environmental footprint, making it a preferred choice for high-performance bevel gears in modern production facilities.